Well, let's continue. If we look to this expressions of pointing theorem, to this expression, or to this expression, or to this expression, we may see that they are all they all are instantaneous quantities. However, for practical purposes, a time averaged quantity is sometimes more useful. Well, we are saying practical for practical purposes, a time averaged quantity is sometimes more useful. So for a periodic time variation of fields, for a periodic time variations periodic time variations of fields, this can be obtained by averaging over a time t. This can be obtained by averaging over a time t, over a time t, which is, for example, period so for a periodic time variation of fields, the time average pointing vector p can be written as, or let's call it p averaged, can be written as 1 over t over the time from 0 up to t, p, which is pointing vector t dt. And it has the units of measurement of watt per meter squared. Always watt per meter squared, the pointing vector. The time average pointing vector is a time average power density. To calculate the total power, either instantaneous or time averaged, the pointing vector must be integrated over the surface through which the power crosses. This usually means a closed surface enclosing a volume. Well, but not always. And the instantaneous power is given as instantaneous. To calculate the instantaneous power, we should take the surface integral of instantaneous pointing vector. So integral over the closed surface S pt ds, or again the integral over the closed surface S, and the pointing vector P is equal to E cross H, or E of T cross H of T ds, and the unit of measurement is watt, and the time averaged power through a closed surface S is given as the time averaged power P average is given as the integral over the closed surface of averaged pointing vector P by ds. It also has a unit of measurement of watt. Okay. If we conclude the pointing vectors, there are several useful properties of pointing theorem and pointing vectors, and they are the following. The pointing theorem gives the power relations of the fields in any volume. The second, the pointing vector is the power density on the surface of a volume. The direction of pointing vector is the direction of flow of power. And the next property is the pointing vector gives the direction of propagation of electromagnetic power. Okay, and last is the pointing theorem gives the net flow of power out of a given volume through its surface. Okay. Let's do some examples. So, consider a plane wave that generates an electric field intensity of E equal to minus y E0 cosine omega t minus kz, where E0 is given, F is given. Propagation is in free space. So first question is, what is the direction of propagation of the wave? The next question, calculate the instantaneous and time average power densities in the wave. Calculate the total instantaneous and time average power carried by the wave. And the next, suppose a receiving dish antenna is 1 meter in diameter. How much power is received by the receiving antenna if the surface of the dish is perpendicular to the direction of propagation of the wave? Okay. Try to think about first question or question A. I think it is not so difficult. Try to think about first about A. So, do you have any idea?
Ustoz Z bo'yicha bo'lishi kerak. Alo. Ustoz
Ah,
Z bo'yicha bo'lishi.
so the question A. We use this equation So, Shabos, tell me your result. How to proceed?
O'tgan safar ko'rsatuvdingiz ustoz X, Y, Z ale tepasida uch burchagi bor. Ale formula yo'q. Oching haligini ustoz.
Okay. You computed the this cross product, yes?
Yeah.
Unit vectors x, y, z,
Yeah.
d dx, d dy, d dz, ex, ey, and ez. Yes. So
X
ex is 0, ez is also 0. Yes.
0.
We have only
Yeah.
ey, and ey depends on z. Yes.
Sure.
That's why this has only one
Matrisa
sorry. Yes. Okay. This
endi
cross
hisoblab
product.
chiqamiz.
Look, this cross product has only one component along x, and is equal to x to the d ey over d
Z.
z. And from the right hand side, it will be equal to x omega
GV
mu, yes, j,
H.
also j mu hx, yes?
Yeah.
And uh, so we need our solution in time domain. This solution is in frequency domain. However, we need our solution in time domain. Sorry, look, here should be plus, but here should be minus. Here on the left hand side plus, on the right hand side is minus. In order to switch from frequency domain into time domain, what we do? First of all, we write phasor form of electric field intensity. Electric field intensity in phasor form is minus y E0 k e k to the power of minus j, not e, sorry, e to the power of minus j k z. And from this we get,
Yes.
sorry, from this we get x
Delta
h is equal to x k over omega mu 0. Okay, we may write mu 0 because we are everything propagation is in free space. Mu 0
keyin uni yozib qo'yamiz epsilonni y0
e to the minus j kz. Yep. Or x 1 over eta 0 e0 e minus j kz. And now
formulaga qo'yamiz.
yes, now we may switch to time domain. In time domain we have x 1 over eta 0 e0 cosine omega t minus kz. Okay, we have defined the magnetic field intensity, and now we may define the Poynting vector p, which is E cross H, which is E in our case minus y is 0 cosine omega t minus kz cross x 1 over eta 0 is 0, so cosine cosine omega t minus kz, and the cross product of minus y cross x gives us z or minus z. Cross product of minus y cross x. gives us unit vector z, and the pointing vector p is equal to z cross e0 squared over eta 0 multiplied cosine squared omega t minus kz. And unit of measurement is watt per meter squared. So we defined the pointing vector p, and pointing vector is directed in the direction of z. So the direction of flow of power is in z direction. This is also the direction of propagation of wave. Okay. The next question. Calculate instantaneous and time averaged power densities in the wave. So, what are the instantaneous and time averaged power densities in the wave?
Integral olib qo'yamiz ustoz. Shuni
Okay, what about instantaneous power density of the wave?
tushunmadim.
Instantaneous power density is simply the pointing vector. Yes, this is instantaneous power density. Instantaneous. If we speak about time averaged, yes, you are right. We should take the integral of over the in our case, integral of over the one cycle. Okay. P averaged. This is P is pointing, not power. P averaged is equal to integral of from 0 up to t of P zt of dt, and is equal to no 1 over t. We forgot about this 1 over t. So is equal to z 1 over t, the integral of from 0 up to t of e0 squared over eta 0 multiplied by cosine squared omega t minus kz. So e0 squared over eta 0 is also a constant, so it also can be moved out of the integral 1 over t e0 squared over eta 0 integral from 0 up to t, and cosine squared omega cosine squared can be written as 1 minus cosine of twice omega t over kz over 2. It can be written in this form, or we can write also, which is more easier or more easier, 1 over 2 multiplied 1 over 2 minus half of cosine twice of omega t minus kz dt. Okay, now let's compute this integral. Okay. One over t is equal to z. Okay, is equal to this. Okay. And so is equal to z. Let me write in a new line. Z 1 over t of 1 over t is 0 squared over eta 0, integral from 0 up to t of 1 over 2 dt minus z 1 over t multiplied is 0 squared over eta 0 multiplied, okay, let's write 1 over 2 integral of from 0 up to t of cosine twice omega t minus kz dt. So the second integral, in our case, if we look to this integral, we are taking the integral of cosine over the one whole period, and integral of cosine over the one period is 0. That's why this term simplifies, and first integral is equal to t over 2, and that's why the average power density of Z, average power density will be equal, in this case, Z okay. First, look to the first term. We said first integral is t over 2, and this t simplifies with this term. That's why average power density will be equal to Z E0 over E0 squared over eta 0. Not E0 squared over 2 eta 0. And if we put numeric values, we have E0 was given was 1000 squared over 2 multiplied. Eta 0 we said is constant, and eta 0 is 377. And this is equal to Z 1326.3 watt per meter squared. This is the average power density. So try to do by yourself the last two questions, question C and question D. Try to do by yourself. And we will discuss the last two questions of our problem in the next lesson. Meanwhile, try to do at home, and if you can do or if you cannot, doesn't matter, we will discuss in the next lesson.